If you were to take a synthesis reaction and run it in reverse, what you pretty much have is a decomposition reaction, where synthesis takes two elements and combines them into a single compound. A decomposition reaction takes that one single compound as a reactant and breaks it apart into its individual elements. After all, to decompose means to break down, to break apart into simpler pieces. Well, if you have a compound that's made up of only two elements, really the only thing that you could conceivably break it down into that are smaller pieces are the elements that are in that compound. The only thing that we have to be really careful for with these decomposition reactions is watching for products, watching for elements that are produced that are diatomic. As we talked about in a previous video, anytime we come across those diatomic elements, we need to make sure to write their formula with a subscript of a 2. But again, with these decomposition reactions, the key identifying feature here is going to be having one single compound as your reactant. No other reactants, just one compound. So let's take a look at an example of how we would predict the products of a decomposition reaction. So let's take something pretty simple like magnesium oxide and break this thing down. As we see, one single reactant, and that one reactant is a compound. Again, something that's made up of two or more elements. Well, kind of a neat little trick here with predicting the products of decomposition reactions is that if you can say the name of this compound, it gives you a really big clue as to what the products actually are. After all, this is magnesium oxide, which implies magnesium and oxygen. And frankly, that's exactly how we should write the products. Magnesium oxide breaks down into magnesium and, represented with a plus sign here, oxygen. Now, oxygen is one of our diatomic elements, so it will get that 2 subscript, where the magnesium is not diatomic, so we'll just leave it alone as it is here. Now, this does not give us a reaction that's balanced, and frankly, rarely will it ever. Regardless of the type of reaction, rarely will we ever get one that comes out already balanced. But that's why we learned how to balance first. To balance this one, our magnesiums are fixed, so we would have to fix our oxygens. We could do that by placing a 2 here. Then we would need a 2 here for this magnesium, a 1 here for the oxygen, and we'd be good to go. So again, biggest thing here is that we pay attention to the elements that make the compound, and then the products are the individual elements, watching out for our diatomics. One more quick example. Let's say I was to take something like maybe iron 3 bromide, because the transition metals are not immune here. If I were to take something like this, well, we'd have to recognize again that this is made up of 2 separate elements, or this single reactant is made up of 2 separate elements. The only thing that this compound can do is break apart into those elements. So iron and bromine. Where iron is not diatomic, it would just stay here by itself like so. And where bromine is diatomic, where bromine is diatomic, we would need to make sure to put the little 2 subscript here. Again, does this give us something that's balanced? No, but we can go back and balance it. We have 3 bromines on the left and 2 on the right. Our irons are already fixed. So what we're going to need to do first is fix our bromines. We're going to move for the least common multiple of 2 and 3 here. That will give us 6 bromines on the left and on the right. And then we'll need a 2 here for the iron to fix this thing up. Again, though, the most important thing with this particular type of reaction is that we recognize first that it's a decomposition by noticing one single reactant that is a compound. The products are always going to be the elements that make that compound. Just be mindful of your diatomics, keep a lookout for them, and that's all there is to it.